No other questions? Well, we've got 2 minutes before I really wanted to start on this, but um, the project today is kind of a fun project. It's something that I've been working on for the past few months and thinking a lot about, and it'll be a fun project to have you do some calculations. Have you had a chance to go on to Canvas and download that file? There is that homework problem. You'll find it under week or chapter 5. Anybody have a problem finding it?
I'm struggling to find it. Where did you say it was again?
It's on Canvas. It's a PDF file on Canvas.
I see it.
You see it? It's on the module chapter 5.
Found it. Thank you.
Okay, great. Okay, my clock is 8:35, so I'd like to get started. And as I was mentioning with people that just maybe showed up just this moment ago, there's been a project I've been thinking about for a while, and the field I'm in is thermal energy storage and just renewable energy in general. And one of the problems we have with thermal energy storage is how do you do it at grid scale? How do you do it at the scale that you can actually store energy at enough capacity that you can fill in the gaps when we don't have the wind's not blowing and the sun's not shining? Where do you fill in the gap? How do you get energy back to be able to continue to produce power? So I've been thinking about this for a while and come up with some ideas. And so what this problem today is based on some of those concepts that have been developed. And so I'm going to start talking about this idea of what I call a dry steam geothermal battery. Okay. So here's the idea. That I'm up here on the surface and somewhere, walking around, and I've got a big solar field out here. And that solar field, let me go to, there might be some big location out here that you've got the field that has been developed, and now you're taking this steam, and say you have double the capacity. Say you go to an existing solar thermal system and you expand the capacity, double the capacity of the solar field, and you take half that capacity and you blow it into the ground using steam. So you generate the steam, you blow the steam down into the ground. And you'd think that wouldn't work, it would just all condense. But that steam pushes all of the water out of the way. And so it's just an energy thing. You put in enough energy into that and you'll create this big steam zone. And looking at what it really takes for something that is really large, figure that it may be 3 months of production from the solar field will have this thing completely charged. And it ends up that when it's big, the heat transfer to the side's pretty small because thermal conductivities of rocks and things, they're not that high. So you don't lose that much heat, especially if it gets big. So that was the idea. And then you think, well, how do you get that to work? I mean, it's kind of crazy. What would this look like? And so go back to this picture of thinking, well, what are the temperatures, saturation temperatures, steam conditions that you would find at different depths below the water table? And why do I say depths below the water table? Well, it ends up that basically everywhere you go below the water table, the pressures in the fluid basically follow the hydraulic head. If I go down 32 feet, I've got another atmospheric pressure. right? So it's just a question of depth. The deeper you go, the higher the pressure, therefore the higher the saturation temperature, right? So here's this curve that tells us, well, how deep can I go? How deep do I want to go? And you start looking at some of these numbers, like this number here. If you talk to the people that inject steam in for enhanced oil recovery, they say that's kind of a limit. That's kind of a limit where they want to go. So I'm interested maybe in this point here. What would it look like here? And it might be easier if I do something up here. It's a little shallower. And if I could still get pretty good efficiency, my developing that field will be much simpler. And actually the energy density is higher there too for different reasons. So anyway, that was the thinking behind it. So where does this come in? Well, to try to think about what we can do in terms of the thermodynamics of this, what we're working with in terms of our saturation steam water temperature and how that relates to what the depth could be that I can actually inject steam and have it stay as steam. Because if I'm going to be on that curve if I'm injecting steam. So that's different. Now, what's interesting about this is that sometimes you hear about these projects like the Forge project that's being implemented down in Delta. That's all what's called this area of enhanced geothermal resources or whatever. And they're all working right here. They're all working right here. And it ends up, in fact, maybe pushing it to here. They're afraid of getting to that line. And it ends up that's a big mistake. They're missing all the good stuff. Anyway, that's kind of the picture of what I've been working on. So how does this come together? Well, if I put this in a big old solar array sort of a system, and if I have a daytime operation, I have this solar array, and I could put some energy storage in here, the big salt tank if I wanted to do that. But say that that's not even here. Say that all those units are not there. So what I'm doing is I'm getting this solar array, and that solar array is taking its heat, putting it into the boiler, going back to the solar array. So all I'm doing is just generating steam at a high temperature and pressure. And then that gets injected here. And then some of it goes over the turbine during the day. Half of it goes to the turbine, half of it goes underground. Then the sun goes down, then this thing gets switched around. And now I'm taking the steam out of this geo battery, taking it straight into the turbine. And if I get rid of all of that, it's not our problem right now. Get rid of all that, then I just go directly from here through that turbine. Now this all goes to a cooling tower. That's all common power plants. And the idea of the cooling tower is to try to drop this pressure back here. If I say that this is P1, T1, and enthalpy 1, right? Because I'm going to be looking at a turbine. So I'm going to be looking at an energy balance here. I'm going to be looking at that enthalpy difference across that turbine. So this state is determined by what's happening here. It's all just coming out at the same pressure and temperature. Go through the turbine, and then through the cooling tower. Now, I have to specify your value of H here. And I'm going to say that H, you're going to be getting that at T is T sat is 25 degrees. Okay, so that's going to set your pressure, P2. And I'm going to say that X2, your quality, is 0.67. Okay, that tells you where you're going to end up in terms of the enthalpy here. So what you're needing to do in this problem is to take on this turbine and say, okay, I know the enthalpy here because I know the pressure and temperature of this. And I know the enthalpy here because I've been given the state, P2, T2, and the quality. So I'm under the dome, right? I'm going to fall under the dome. This actually would be the case if I have what we call an isentropic efficiency of the turbine of 0.88 or 0.85, which is pretty reasonable. But that quality isn't reasonable. They really want to run those turbines so the moisture content doesn't exceed 88%. And that's, it's beyond that now. So the quality has to be above 88%, and the quality here is only 69. Now, they've got turbines that actually remove that moisture, and they're ones that are special for taking saturated conditions. This is a system would put in superheat, and we'll talk about that a little bit later. But there are turbines that will take geothermal energy directly to the turbine and they condense out the water. They drain the water out that condenses so that they don't run into problems with the turbine. But the thermodynamics is still the same. Okay, so we've got this condition here, exit quality. We have this value of H that we're going to be getting from here, and then we're going to get two different values for the pressure here, for what's conditioning the pressure here. And what am I really going to know for the enthalpy from that geo battery? I know the pressure, right? And so if I know the pressure and the temperature, I know the enthalpy. So I'm specifying that at two different depths, one at like 400 meters, the other one at 800 meters. And from those two different depths, we're going to get different pressures and temperatures. And I want to know what effect that has on the efficiency of the process. Okay, so when we look at our problem, so creation of an artificial geothermal reservoir for energy storage has been proposed. Okay, so two different depths are being considered. One about 400 meters below the groundwater surface where the pressure is 4 megapascal. Oh, that should be a lowercase a, sorry. And the other at 800 meters below the groundwater surface where the pressure is 8 megapascals. Saturated steam is produced when energy is returned to the surface. Okay, so if that saturated steam is fed to a steam turbine, how much work in terms of like kilojoules per kilogram? Then I could just multiply that by my mass flow rate coming from the field, and that will give me my total energy production. But what I'm looking for here is just like, well, how much energy per kilogram of steam am I going to be able to produce? And so I'm going to feed that into the steam turbine. Steam at the exit of the turbine. The quality. Excuse me. Steam quality at the exit of the turbine is 67%. Oh, I've already put it here. Never need to read on. At a pressure equal to the saturation pressure for 25 degrees C, right? So defining thermodynamic. So you want to be doing that for those two different cases. So let's get started. What are we going to do? What's the first thing to be doing here?
Quick question, Professor, about how this is set up. Is the pressure at the geothermal battery, which is in the first case 4 megapascals, that value, is that the same as our P1 that we're looking at before it goes into the turbine?
Yes, it is. Exactly.
Okay.
And so we're looking at the two different cases. And what you'll find is that the temperature at 4 megapascals is about 250 degrees C. The temperature at 8 megapascal is about 300. So what we'd like to do then is maybe put together a little table that has the different states, state 1 and state 2, and start putting in the information that we know, temperatures and pressures. And in this case, we know that what we're going after is going to be the enthalpy. So we'll be looking at the enthalpy at those two pressures, saturated steam enthalpies at both of those pressures. Right. So where are we going to find those?
We need to go to the steam tables for these.
Yep. Which steam table?
I think it's A6, I think it is.
The saturated water table.
Yeah, it's saturated water table. And where do I go on the saturated? Which one of those two tables do I want to use? The temperature tables or the pressure table?
Pressure.
Yeah. So giving you pressure. Okay. So you go to the pressure table. So what is the enthalpy coming into the inlet of that turbine? Anybody find that number yet? I ought to be giving prizes for the people that can find the number in the steam tables most quickly.
I think I got it. Is it 121.39?
No.
For pressure 4?
It should be 2800.8.
Correct. 2800. We're looking at 4,000 kilopascal, right? 4,000 kilopascal is a megapascal. So you go to the pressure of 4,000, and you look across that, you see, I gave you a hint, 250, right? So
Oh.
250.35. And you go all the way over to the enthalpy of the gas, the enthalpy of the vapor, and it's 2800.8.
I completely was looking at something totally different. My bad.
Yeah, that's okay. These are all just opportunities for us to feel like we can go to the steam tables and it would have to make some sense, right? The enthalpy should be pretty high because it's going to be. And so you look at the steam tables and you look under enthalpy and you think, oh, this is the vapor enthalpy, saturated steam enthalpy, and you look at those numbers and say, oh, those are like over 2,000, all of them. So, and that's a part of also getting some intuition. That's what those numbers should start to look like. And a lot of it just looking at these tables and just thinking about how they all relate and how the internal energies fit with the enthalpies and how that all fits with the PVT information. Okay, so we know the inlet. What about the other pressure?
$2758.7.
Correct. Okay, and isn't that interesting? You'd think that at higher temperature, the enthalpy would go up. We're not that far from the critical point here. So critical point is 373. Yeah, it's 374, and actually so your enthalpy of the vapor actually drops. It hits a maximum. It ends up to be at about 218 is where it hits a maximum. Okay, 218 degrees C, pressurized to about 2.25 megapascal. Okay, so we're kind of on that place where you're getting some high enthalpies, but you're not getting much of a benefit by going to higher temperatures and pressures when you get to this point. Okay, so when we look at the amount of work that is coming through, what are we going to define as the quality of the exit? What do we define as the enthalpy of the exit? I guess I should be saying. Where is the enthalpy at point 2? I'm giving you a piece of information there, right? And that information is this piece, right? 25 degrees, right? Saturation pressure, 25 degrees. So how am I going to find the enthalpy of that steam that comes out at 67% quality?
Add the enthalpy of the fluid plus the quality times the enthalpy of the difference between the fluid and the gas.
Exactly. So let's go to the temperature tables now, because I've given you a temperature of 25 degrees. And at 25 degrees, we go across, and what we find is that the enthalpy of the liquid is 104.83. What is the enthalpy of phase change?
2441.7.
Correct. So what's the enthalpy of the exit?
Professor, are you writing anything on your screen right now?
No, I'm not. You want me to?
Oh, well, someone just asked in chat, so I was just making sure that we weren't missing it. Also,
No,
the enthalpy I
no.
got was 1740.
1740. Can anybody verify that?
That's about what I got.
I got the same thing.
Okay. All right. Good work, team. So what do we get for the work being produced for each of those different cases? Okay, anybody have a number? Want me to help you with the first one? 2800.8 minus 1740.
1060.8 is what I got.
1060. Okay. Somebody verify that?
I got the same value.
Okay, great. What about at 8 megapascal?
$10.17.
Okay. Kind of interesting. You think, oh, you should be able to get a great benefit, maybe by going deeper. And doesn't seem like you necessarily would. It ends up that you do, but it doesn't seem from that calculation that you necessarily would. Okay, for those two different values, one of the things we like to define on these systems would be the thermodynamic efficiency. And so we'll define that with this expression here of eta, our value of eta, which is the work that we've calculated, the work that we're getting out, divided by the energy that has the heat energy that has gone into the system. And now the heat energy is always referenced to something. And the place that it is referenced to always is going to be the base case of where the whole system started. Remember in my figure that there is that water storage tank is that steam comes out and condenses and it gets stored in the tank, and then that gets fed to the steam generator. So the enthalpy of that fluid, so that's the enthalpy of water at 22 or 25 degrees, saturated water at 22 degrees is the value for that. Okay, it always goes back to the base case. So I start there and then I add heat to be able to get to H1 to be able to power the system, right? So the heat that I'm putting in is the difference between the enthalpy of that fluid that is going into the turbine, but based on the enthalpy when that steam was back as a condensed state in that tank after the cooling tower. Okay, so what is the efficiency for those two different cases? First of all, they're not going to be a lot different because those differences in enthalpy, that's the only thing that is really changing here, right? That enthalpy is not changing that much, but let's do the calculations on it. So what is our value of HO? And I did just tell you that. So when you're looking at those steam tables and you're looking at that value of H, why don't you just take a little bit of a look at the difference in the liquid enthalpies versus the liquid internal energies. And just another verification is, oh, okay, great. You know, C sub P is equal to C sub B. It doesn't really matter. Enthalpies, internal energies, they're the same thing with liquids and solids. Okay, I need a calculation. Somebody give me a calculation for the efficiency for the 4 megapascal case.
.393.
Okay. And what about for the other case?
For that one, I got 0.383. Did I do something wrong there?
383.
Yeah.
or not, sorry, for the same one that I think Michael just said. For
Oh, yes.
the
Yeah,
0.93, I got 0.383 instead.
Yeah, right. So I'm just going to have those numbers both out there. I'm going to erase one of them. I'm going to wait for some more verification on what that number actually is.
I got 0.393.
Okay. So we'll just go ahead and go with that one. Okay. That's for the 4 megapascal. What about for the 8 megapascal?
I got 0.384.
I can confirm that number.
0.383 what?
84.
Okay.
So
that's
I have one question.
Yes.
Can you repeat where you got that H naught from?
Oh, that's H naught. Yes, if you go to the steam tables under a temperature of 25 degrees. So see, this is so I'm looking for HO. I'm looking at the base case from that water that is in the tank and being then boiled to get made to an enthalpy of H1, right? So if I look at the temperature at 25 degrees on the saturated water tables, and I find that the liquid internal energy is 104.83, the liquid enthalpy is 104.83. You know, both of those are listed in table A4, the saturated water temperature table.
Perfect. Thank you.
You're welcome.
Professor, what were you using for H sub 1 for your efficiency calculation?
Well, we have those two different numbers. One of them was the number 2800.8, and the other was like 27. Let me see if I can pull that.
1740.
It was 2758.7.
What?
Okay, those are the vapor enthalpy at saturated conditions at 8 megapascal, and then the other one was at 4 megapascal. So the temperature at 8 megapascal is 295.01, close to 300. Okay, you see it?
Yeah, thank you.
Okay. Any other questions on this? Well, let me just give you a little bit, see if I can pull this off here. Let's bring up another figure, because this one's kind of an interesting figure too. Now, there's another part of this that is an interesting feature of what happens. And it's not trying to get this sent airdropped. Oh no, my airdrop doesn't seem to want to work. Okay. So there's a different curve, and we'll be talking about this a little bit later in the semester. There's another property that we haven't talked about that is called exergy. Some people call it availability. Some people call it Gibbs free energy. And we'll be learning about that after we learn a little bit about entropy. But what Gibbs free energy gives us is that it provides information on the capacity of that fluid to be converted into work. Okay, or if I put work in without any losses, all I'm doing is increasing the exergy. So this thing of exergy is the potential to do work. So when we think of it in that form, if I want to look at the true efficiency, that I would look at this thing called exergy divided by that enthalpy difference that we just used in our calculation. And if you do that, you have a little bit different picture. And the picture comes up to look like this. And if I look at the depth below the groundwater, this is going from 0, and here's this one target here, which is kind of, gives us about 250 degrees out here. It gives us an efficiency, these numbers that we're calculating. But if I go down to this point here, I'm all of a sudden, I'm showing thermodynamically that I should be able to get higher efficiencies at that higher temperature. And this first calculation ends up not telling us that that is indeed the fact. And it's been interesting to try to match those two things. It ends up that the conditions at 300 degrees will provide higher power output. And part of it is because the quality on the exit is higher, right? So, the quality on the exit is lower. And if you think about it on a PV diagram, if you're kind of up there, it drops at a point which is at the high temperature at a point which the lower temperature kind of extends it out. So it ends up that you do get a better efficiency at when you go up to the 300 degrees. And you can see this in terms of what we're looking at in terms of this maximum theoretical conversion efficiency that looks like that first calculation missed a little bit of information. And what it missed was that piece that had to do with the entropy term associated with the conversion. And so we haven't seen that yet. So we haven't seen that we can actually push this thing even farther. And so the place I'm looking here, again, maximum they've been able to do for steam injection. And the scale of the system that I'm looking at is something in the range of 1 million cubic yards. Again, I'm looking for grid scale, the energy storage. So if I have something on that scale, these calculations show that I could push something close to 100 megawatt power capacity. And you can run that 24/7, because what you're doing is taking half that energy during the day, putting it underground, taking the other half of that energy and putting it through your power system. When the sun goes down, you just keep producing the steam directly from the ground, and the system shouldn't shut down for a moment. So you can run 24/7. That's important. The biggest problem we have with converting to renewable energy is trying to find ways of storing energy so that we can use it at the time. I mean, look at where Texas is now. You're like, what? You've got to have some storage capacity to be able to have a resilient system. So this, as far as I can tell, is the best way that we could possibly do it. And what it does is it matches the best output from the solar field with the best method of storing it underground. And I should say that the numbers that we're calculating from these things are coming out, the number you calculated today are really very good numbers. The best geothermal reservoirs in the world produce at an efficiency of 21%. Right? And they're working up there.
Could I ask a question, Professor?
Sure.
I don't know if you've heard, but there was supposedly a geothermal energy source that caused a earthquake. I think it was somewhere in the Asia region, and they said it was due to trying to harness energy in this manner. I don't know if you've heard anything about that. Or
yeah. Yeah. And let me explain that. That's an interesting sort of a segue to another interesting thermodynamic piece of this. The intent on what they've been doing on hot, dry rock, and I showed you where they were on the temperature scale, or where they were underground. They're all working on this line. They're looking at only liquids. So the transport of energy between liquids and the surrounding rock is really, really difficult because it's all going through fractures, right? So they have to put in a bunch more fractures to be able to get any heat transfer from that rock to that flowing water. And so they have these two wells that are put in, and they've got these wells that might, a well here and a well here, and they're injecting, cold water here, and they're, getting hot water that's coming in here. And there's these fractures all over the place. Like, are they going to intersect? Is all this water going to go up here and down here and miss all of that rock? So what they do is they come in and hydraulically fracture it, and they come in and they just bring the pressure in this injection well. They just bring that thing way high and just create these fractures to go like that. And they create the same as fracking. And so they inject under really high pressure. So the pressure is greater than the weight of all of the soil above it, all of the material above it. And if you can lift that up with the pressure of the fluid, then that fluid goes in and they put in like a gel that's carrying sand with it that just keeps those fractures open. Okay, so that's all fracking. It's all fracking, and that was what was causing the problem. I wouldn't even be thinking about doing that. Like, there's no need to, because, see, steam operates differently. We know that temperature and pressure are connected, right? Temperature changes, pressure has to change if it's saturated liquid vapor system, right? But what we have in these subsurface environments, we have steam and water and a lot of mass in the rock. And what we can do in terms of storing the steam is really very simple. I just bring up the pressure in that steam zone. If I'm bringing up the pressure, I have to bring up the temperature because they're connected. To bring up the temperature, I have to get energy from somewhere, and it gets it from condensing steam. So essentially what I've got are these condensation waves that are propagating through this material. Okay, so it's, and what's so interesting about it is that it isn't necessarily following the pathways between two wells. It's going to be finding the coldest locations in that media. It's going to be going off on these side fractures. It's going off in all kinds of directions, wherever it can find a pathway to finding cool rock. That's where it's going to go, and it's going to condense. And then all of a sudden I drop the pressure and say, oh, wow, it's a little bit hot in here. I'm going to come back out. So the problems they have here with these fractures and trying to get it to happen, I don't care. Steam's going to come in, it's going to go up that fracture, down that fracture, and it's going to be harvesting steam from the material adjacent to each one of these. It's almost like the analogy I use for this is a lung. Because it's not like you're just, because so much of that steam condenses, it's like when your lung expands, it has more capacity than just a solid capacity. So you inhale and you're taking that air down through the biggest channels, and they're going into smaller channels, and then that finally ends up at the final parts of your lung where you have the smallest pieces. And then that's where the mass transfer is occurring. And then you exhale and you push that back out, and all of that breathing comes back out. And that's essentially what happens when I'm doing the steam injection and withdrawal. The pressure comes up, all that steam condenses, I drop the pressure, and all that steam comes back out. Now, again, you'll learn something about this as we start talking about entropy production. But it ends up that this works really well, in part because I'm transferring a huge amount of energy with relatively small temperature differences, right? That steam comes in, it sees temperature differences, maybe a couple, 4 degrees C. That's all it takes for getting the storage that we need. So the temperature differences coming in and out are really small. That gives us really a high exergy exchange. That's why it's working so well. Anyway, kind of an interesting thing that I wanted to bring up, because I've been working on this, and I felt like this is really an interesting thermodynamic problem, contemporary. It's out there. It's something that I just got the paper finished last night or last weekend, and thought you'd want to look at that because there's a lot of fun thermodynamic aspects to that. And also I wanted to have you have a sense that what you've learned so far, you can apply to, simple a little bit, yeah, but you can apply to these kinds of problems. Okay, each one of these units, each one of these is a first law energy in, energy out. A heat exchanger, right? I've got energy coming in the geo battery, and I've got energy coming out. It now would be superheated steam. I've got a heat exchanger, the salt tank that has this heat exchanger here. I've got fluid coming in here. I've got hot salt coming in here. I've got cold salt coming out here. I've got hot steam coming out here. So you've got, hot oil coming out here. So you've got all these different, each one of these different units here is a control volume. And every one of these, except for the geo battery, that thing is a transient. That doesn't look like a steady state process, but everything else we're modeling as a steady state. We've got a cooling tower, right? We've got a cooling tower. We've got a mass flow rate coming in, and that same mass flow rate is going to be coming out. I'm also going to have air coming through here, right? So the air that comes in is the same as the air that comes out. So again, these are just mass balances and energy balances. Summation of masses going in will equal the summation of masses coming out. Summation of energy going in will equal the summation of energy going out. So what I'm doing here is I'm taking energy out of that condensing steam, and I'm putting this in a cooling tower so I can condense it all out. This is just a big condenser. And so now I'm taking air that is in at ambient air, and I'm actually adding water to it. So I'm getting like this evaporative cooling so I can get to an even lower temperature. So I want that pressure as low as possible. So as I go through here, I'm adding a little bit of water. I've got coming in here is cool air, and coming out here is completely saturated warm air. Okay, so again, that's just a example of it, just another heat exchanger and another summation of masses in, masses out, and summation of heat in equals heat out. And so since we're taking out so much energy here, then we cool it down to get to a low temperature, 25 here. The boiler, the same thing, energy that goes in, probably through heat. We've got a massive water coming in, and we've got some massive steam coming out. Mass of water in is equal to the mass of steam out. So each one of these devices, except for the storage tank and the geo battery, those all you should be able to handle energy balances on each one of those. And you should be able to do a mass balance on each one of those. And you should be able to look at energy balances in a way that you could do things like calculate power, or if that were a turbine, to do work. And so those devices that I talked about on the video that I posted, and there's really only 5 devices that you need to think about. This is one of them, a turbine. Somebody else give me another one. What other device that have I been talking about that would be, looking at the steady state flow energy equations and mass flux?
Was another one funnel, or did you say like a nozzle?
No. Yep. Okay. We have a nozzle. We have a turbine. What else? A compressor, right? 2 more.
Pump.
A pump, right? And 1 more.
Was that the valve?
It's not throttling valve, right? Those are the 5 things that you need to see. If you understand those 5 things and be able to apply the equations to be able to get the work out, work in, the velocity coming, that understand the enthalpy is equal on either side of the throttling valve. If you've got those concepts down, you're going to do fine. Those, because everything that we're talking about from here on out is just a combination of doing these energy and mass balances around different devices. Okay, so just sort of, if you're thinking about what do you need to understand to be able to do well in the rest of the class, if you're to the point now where you can go through this homework problem, figure that out, understand how to use the steam tables, understand what this means, and what that means in terms of P2, and what that means in terms of getting my H2. If you can do that, you'll be doing fine. And to be able to understand how do you get that power, and what energy in or energy out is necessary to get a particular change of state that we might want going from one place to the other. For instance, how much heat do I need to be putting into the boiler to get a mass flux of water to be turned into steam at a given temperature and pressure, right? And that's pretty simple. We already know what that is, right? We know that is, coming in at, what do we say, that we're looking at this thing as being at an enthalpy coming out at 2808. we've got an enthalpy coming in at 104.89, right? So we already know what that would be. And so those are the kinds of things that you really should feel comfortable with at this point. And if we have these down, we can do the energy balances. And if we can do the mass balances, then the rest of the stuff starts to flow. Really, the thing that we're going to be, the big difference of what you're going to learn in future part of this class, it's only this. It's only how do I get 0.67, and you'll get there. But that's not a difficult calculation either. Once you get to the point thinking, oh, this is how I'm going to do it. We're not there yet because they haven't talked about entropy, but that's what you need to know at this point: energy balances and mass balances. And you've got, again, a couple of different things you're looking at. You're not in this problem; these are all steady state flow process, but. And then we'll be doing on a review. We'll go back and look at some of the things we've talked about for control volumes in terms of, again, the same thing, finding different properties on the steam table, being able to write out the equations for, in our case, for control if it's really an equation for the work, okay? So that's kind of and I guess to what I needed to talk about today. Anybody have any questions?
For the exam next week, are these type of Friday problems harder, easier, or comparable to what we could expect to see on the exam?
Harder.
Okay.
Yeah. No, these are harder. These are meant to be active learning kind of exercises, meaning that I would not expect you to know how to do this problem before you come to class, but I want you to know how to do the problem when you come out of class. Right, so that's really the objective, and that's the way that I try to set up these Friday problems to have us go through kind of joint thinking process of what we have to consider, and to be able to take on a complex process like this and to break it down into something that we can get a pretty nice calculation. We've got efficiencies out of this thing that are better than the best geothermal reservoirs in the world. I mean, so just to put that in perspective of what you've just calculated. All right. So anybody else have a question?
I guess I have another one. You said this is better than any one in the world right now. Do you think that in practice, like if you were to apply this, do you think that you would see the same efficiency coming out as you calculate, or do you think it would be much less? Because I know sometimes like we see in calculations things go very well, but then in practice there's a big struggle to keep the efficiency that we calculate, if you understand what I'm trying to say.
Oh yes, yeah. I mean, there are a lot of pieces to this. What we've shown here is a relatively simple analysis. Let's see. Hope we get back from there. The biggest problem in these power plants is going to be the efficiency of the turbine, and that's where all the work goes. Because I can increase that efficiency 1%. That's a huge deal in terms of my money, right? So I'm only running at like maybe 30, 40%. And if I can get another, 2 or 3 or 4% is like, I've got 10% more profit for it, right? For the same cost, I get 4% more energy, more profit coming back in. So working on the turbines has been the biggest issue because they're not 100% efficient from the standpoint of what we call entropy. We can't convert that thermal energy so completely to the kinetic energy within that turbine blade to make it spin. So we do have the turbine is our biggest issue. The other issue that you typically have in power plants, I kind of hinted at it, and it may be a little bit early to be talking about it, but it's this thing called exergy destruction, the things that destroy your capability of converting to power. And those are things like heat transfer over big temperature differences, which is why the liquid efficiency that I showed the steam efficiency, but also on that same curve, I showed the liquid efficiency. You just can't transfer the energy out of there at a constant temperature like you can steam. I can condense steam and I can transfer energy out so effectively. I just have to cool the water off. The cooler I make that water, the less efficient it's going to be. And so you have some fundamental problems with using hot water for that power production versus using straight steam. And so that was another part of the problem of, well, how do we get the efficiency of the overall system up, right? Because trying to make steam or making hot water from that solar field, pumping it underground, and having it come up with an 11% efficiency on conversion, and some real problems with groundwater, because as you increase the temperature in the ground, the solubility of the minerals go up, right? So you heat that up and you bring up this water, and it goes into your condenser or into your evaporator or into all your equipment, and you cool it down, and all those minerals precipitate out. It just fouls everything up. So, it's a real problem working with water, and they're only getting 11% conversion efficiency. So but that's a place where the effort really should be spent. Saying, well, how do we find a combination, integrate these different technologies so that our exergy, our overall exergy throughout the process stays as high as possible? That's going to give us the best overall efficiency. The things that kill exergy, heat transfer across temperature differences, heat losses, inefficiencies in turbines, pumps, that type of thing. Okay? That's maybe a long answer to your question, but it's a great question. What do we do about these systems to be getting the most out of them, and what kind of an approach do we take? And I think kind of hinted in this presentation that doing it the conventional way might lead you to kind of a misleading answer. Under the basics, the maximum power production is a difference in Gibbs free energy, that you come to a little bit different conclusion. And you'll be seeing the power of that as you get further into the class and we start talking about that section. And we'll go back and look at that availability calculation on this problem again. All right. Those are good questions. It's and really thermodynamics, what we're doing in this class and what we're learning in this class is really about that. How do we use our energy more efficiently, and how do we get energy without burning carbon and putting that carbon dioxide into the air? I mean, we've got some big questions to be answering in the next few years, and it all goes back to basic thermodynamics, which is why it's so exciting for me to be teaching this class, because I know that there's a new generation of engineers that are coming out that maybe have a really good perspective on the challenges and what kind of capabilities we have, and the importance of what you're learning in thermodynamics right now to go forward into say that this stuff really works. This helps me do my job. This helps me live in my environment better. This helps me come up with new ideas or better ways of doing things, being more energy efficient. And so that's really the basis of it, is a good understanding of thermodynamics, both potential and where we lose our efficiency, what things hurt the performance of the machines that we build. We build a lot of machines as mechanical engineers, a lot of machines that keep us warm, cold, and and get our cars to run and our airplanes to fly. We build a lot of machines, use a lot of different kinds of energy, and that's really the basis of mechanical engineering, is taking the different forms of thermal energy and creating new things that use that energy in creative ways. So, and the basis though is still thermodynamics. Basis of a steam engine was thermodynamics. Thermodynamics was based in some way with the invention of the steam engine. Okay. Long discussion. I'm just sitting here talking all the time, and I'm glad that I got a few people to get some questions answered. And thank you, or get some questions asked. And thank you for the work on getting those calculations done. Those were pretty informative. Any other questions before we leave? And again, this homework will be due at tonight at midnight. Okay.
And Professor, did you say you would try to issue a practice exam?
Oh yes. I'm going to be putting out a practice exam over the weekend. Yes, and then we'll be going over.
Try and work over some of the problems and go over some of the homework problems. Just kind of rehash them. Try to just do it. Work the problems by memory, not rely on notes, and just make sure we have them down.
Yeah.
Okay.
Yeah. That's a good way of doing it. And I will say also that one of the things that's really I do like about the book is the back of the chapter. There's a review page. Any equation you're going to be needing for a test or anything, it's going to be on that review page.
Mm-hmm. Okay.
They're like a cliff note. Think of them as the cliff note of the chapter, and understand the chapter, but if you want to get to the meat quickly, go to those reviews. That's where the equations, and they're pretty well explained.
Okay.
Right.
Well, very good. Well, thank you very much, Professor. Appreciate
All right.
it.
You're welcome.
All right. We'll see you.
Okay. Bye.
I have a question.
Yes.
Did you just say that the homework's due tonight at midnight? Because on
No. Oh, excuse me. The in-class homework. Yeah.
Oh, in class. Okay, gotcha.
Yeah, and I've extended it. I don't know if it's been that date has been changed on Gradescope. I'll double check that. I know that I changed it on Canvas, so I postponed the homework till Monday, but just the Friday ones. The Friday ones, I just want you to focus on.
That.
Should be able to get it done in class.
On Gradescope,
Get it done in class, and to do it maybe a couple of adjustments before you hand it in if you have something right after class. Right.
Awesome. Thanks.
Good. You're welcome.
on Gradescope, it still says due tonight, just so you're aware. But
okay, I'll send off another message to the TAs. Thank you.
okay, thank you.
Yeah. Okay. Oh yes, full points. Do full points on Monday.
Thanks, Professor.
Okay. All right. Goodbye, everybody.
Are we still have